Hello and welcome to Lecture 11 in Electrochemistry. Today we'll look at cell stoichiometry. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis for the bulk of diploma exam questions that you'll see. Hopefully you've been tracking these knowledge outcomes as we've moved through the unit and you get a sense of how well you've mastered the material. We start this discussion with a consideration of the concept of electric charge, symbol Q. The units for electric charge are the coulombs, symbol C. Thanks to the work of Millikan and others, we know that one electron carries 1.60 times 10 to the minus 19 coulombs of electric charge. If we multiply this by Avogadro's number, and we determine that 1 mole of electrons carries 9.65 times 10 to the 4 coulombs per mole of electrons. This is referred to Faraday's constant, F. It means that 1 mole of electrons carries 9.65 times 10 to the 4 coulombs of charge. And when presented with a charge, then we can determine moles of electrons by dividing total charge Q by Faraday's constant F. Moles of electrons equals Q divided by F, where N sub E negative is number of moles of electrons, Q is charge in coulombs, and F is Faraday's constant. Current is symbol I is a measure of charge Q per unit time, and it is fundamental units of coulombs per second, or amperes, and we calculate it using the following: I equals Q over T. Current equals charge per unit time. Q, of course, is charge, I is current, and T is time. The above equations can be combined into one equation, and we can use these equations in stoichiometry to calculate current, time, mass in moles of a substance, and moles of electron. And here's when we bring the two equations together, we get N sub E equals IT over F. And this work has tremendous practical application in industry. And we'll examine a few questions, give you a sense of what I'm talking about. First question, determine the moles of electrons supplied by a dry cell supplying a current of 0.100 coulombs per second to a radio for 50 minutes. So, as in all problems in this course generally, we start with our formula, N equals IT over F, and then we substitute into the formula. So, moles of electrons, N equals I, which is 0.100 coulombs per second, times 50.0 minutes, which is the time interval we're given. We need a conversion factor there to convert from minutes to seconds, and of course there's 60 seconds in 1 minute. So all of that represents the numerator. The denominator is F, it's Faraday's, 9.65 times 10 to the 4 coulombs per mole. We get a raw value of 0.0031008 moles of electrons. Significant digit analysis appears to require the use of 3 significant digits, so our final answer is moles of electrons equals 3.10 times 10 to the negative 3 moles. In English, the dry cell supplies 3.10 times 10 to the negative 3 moles of electrons. Let's take a look at another. What mass of copper is deposited at the cathode of a copper refinery operating at 12.0 coulombs per second for 40 minutes. So here we're looking at, a small-scale industrial process, and we want to determine the yield of copper from operating a refinery. Start with the same formula, moles of electrons equals IT over F, and substitute in. So there's our current, 12.0 coulombs per second, times our time interval, 40 minutes, times our conversion to get out of minutes and into seconds. 60 seconds is 1 minute. So that's our numerator, divided by Faraday's 9.65 times 10 to the 4 coulombs per mole, and we get 0.298445559 moles of electrons. The next piece, we have to get out of moles of electrons and into mass of copper. And that looks like this. The mass of the copper equals the moles of electrons, 0.298445559 moles of electrons, times the conversion factor. 2 moles of electrons generate 1 mole of copper. And if we think about it, the most common copper ion is the copper 2 ion. So the assumption we make here is that we're reducing copper-2 ions into solid copper atoms, neutral copper atoms. And then we multiply by the molar mass. 63.55 grams is the molar mass of copper over 1 mole of copper. So this string of conversion factors gives us the mass of the copper generated, 9.4831088,129 grams of copper. And again, sig digs analysis indicates we require 3 sig digs, so the mass of copper produced is 9.48 grams. In English, 9.48 grams of copper are deposited at the cathode. Again, here's a question related to silver being deposited on objects in the silver plating process, an electroplating process. And the question is, if 0.175 grams of silver is to be deposited from a silver cyanide solution in a time of 10 minutes, predict the current required. So here's some sense of your electrical budget to do some copper plating. Start with the same equation. This time we're going to rearrange it. We need to isolate for current, which is what we're looking for. I equals NF over T. We don't have moles of electrons, but we can derive moles of electrons from the mass of the copper. We know that we want to lay down 0.175 grams of the silver. We know we want to lay down 0.175 grams of silver. And we convert that into moles of silver. 1 mole of silver over the molar mass, which is 107.87 grams. And we want to convert that into moles of electrons. And we know that silver forms a 1+ ion. So the stoichiometric ratio between the silver and the electrons is 1 to 1. And then, as the equation calls for, we multiply by Faraday's, 9.65 times 10 to the 4 coulombs per mole. And all of that is the numerator, divided by time is the denominator. And we're given a time interval of 10.0 minutes. Of course, we have to convert that into seconds, and there's 60 seconds in 1 minute. So the current required is 0.260923648 coulombs. And again, applying significant digits, that's 0.261 coulombs. In English, we would say the required current is 0.261 coulombs. So I wouldn't say that the mathematics is particularly difficult, but it has tremendous practical application. So I'd refer you to any homework your teacher assigns in this matter, and I hope you find this video of help. That actually concludes my lectures in electrochemistry. I'll see you next time when we talk about introductory equilibrium principles. Fascinating unit. Thank you very much.